Okay, so hello everyone. Welcome to another session of Coffee O'Clock. I'm your host Akash Kundu, and before starting the event, let me make a small announcement about one of the incredible pillars of Q India. It's called QSafe, and in Q India, we give the safety of our beloved attendees and the participants. Like we give so much importance to that, and this is our one of the aims to make sure that they are safe in all the events at all levels, right? So that's why we have this QSafe part, like a pillar in Q India, and they make sure that you are going through everything smoothly and you're not facing any kind of problem during the event. So, but you can help us to strengthen this, make this pillar stronger by involving yourself in a very small form, which will take 2 minutes of your time. And this form, I would like to say that it's fully private and anonymous, so you can just be fully honest while filling up the form and about your experiences which you're going through in the events and stuff. And it will help us to understand that what is your experience during this kind of event. So I will be really grateful if you kindly go through the form, which I'm going to share in the chat soon, and just give us your 2 minutes. Thank you. So this is like one of the announcements I wanted to make, but let's go to the event, right? So once again, I'm Akash Kundu. I'm a PhD student at Polytechnic of Science, and I'm your host. And today we have Rajiv once again as one of the speakers, and he's going to talk about quantum arithmetic. And he already talked about like an introduction of it. Right? Today he's going to give like an implementation and practical applicability of it in a more detailed manner. So Rajiv is a researcher currently at QuantumBasel, and so let me just welcome him once again, and thanks Rajiv for accepting to give a talk after a long time. We are starting this event, so thanks, and the floor is all yours. Please.
Thank you, Akash, and it's nice to be back. Thank you for having me again. Hopefully that means my first talk wasn't completely terrible, so I'm glad to be back for the part 2 of this. Let me quickly share my screen. Here we go. So as usual, if there are any questions, please feel free to write them in the chat. There'll also be time at the end for questions, but of course you can unmute yourself and interrupt me at any time. That's no problem at all. And for those of you watching at home, part 1 of this talk, the link is in the description below. But even if you haven't watched part 1, I'm going to give a small recap of it before moving on to the rest of it. So let's start with a small recap. So we're talking about quantum arithmetic. So quantum arithmetic is basically the study of how to perform arithmetic on a quantum computer. And we're talking about it from the algorithms perspective. So what I'm going to be talking about mostly is this unitary that performs a quantum arithmetic operation. So you have some U of F, which is some unitary. It acts on some input operator X and some output input register X and output register, which is often initialized at 0. And it does nothing to the input register, and it encodes F of X in the output register, where F is some function that takes in a real number and spits out a real number. So that's kind of my hand-wavy definition of an arithmetic function. And this is interesting because oftentimes the quantum arithmetic part of a quantum algorithm is a costly overhead. So you would never use a quantum computer to perform only arithmetic. If your goal is just to compute something that just involves arithmetic, you would just use a classical computer. But sometimes, longer end-to-end quantum algorithms contain quantum arithmetic subroutines. And so working on these, trying to understand how to reduce the costs of them is interesting because it pushes quantum algorithms to become more viable. One other thing I'd mentioned last time was that the numbers, so I've mentioned in this top part that the number X is just encoded in this register, and that this encoding, though, can be done in different ways. So here's an example of an encoding. It's in a fixed point register. And this sentence just says that 0011 represents 0.75. It's not, for the purposes of this talk, it's not important to know exactly what a fixed point register is, floating point register is, but just to know that when working on these unitary operators, it will depend on the type of encoding that you have. So the operator can be different depending on the type of encoding. And the last point that I made last time, or the last important point I would say that I made last time, was generally when working on quantum arithmetic algorithms, we work in a fault tolerant regime. So whenever we talk about costs, we look at T depth and T count in terms of the circuit depth and circuit gates. Okay, I'm happy to go over any of these if there are any doubts at all. So don't hesitate to ask. But for the rest of the, there we go. For the rest of the talk, this is what I'll be talking about. So I will be talking a little bit about our work that looks at how to implement any single valued arithmetic function using what's called the lookup table subroutine. So this is the work, this lookup table is the crux of what we then use to do our work, which I'll talk about. So you just, again, implement the same function, but it's quite general in the sense that it's a recipe to implement any function that looks like this, which takes in a real number as an input and outputs a real number. And then I'll briefly discuss a real-world use case. So I won't go too much into the use case itself, which is Monte Carlo simulation for derivative pricing. I'll just show a little bit how it is, how quantum arithmetic is part of that use case. And actually, this Monte Carlo simulation for derivative pricing use case, there are other talks there available on YouTube, and actually one of them was given by myself. So that's the reason I won't go too much into depth, because there's already a lot of material out there, and also understanding the exact intricacies of the use case is not paramount to understanding, how quantum arithmetic fits into it. Okay, so after I've discussed the implementation and an example in a real world use case, I'll talk a little bit about the cost of this implementation and talk about how, for example, for the function e to the minus x, it turns out, surprisingly, at least in my opinion, surprisingly, it is the most efficient way to implement this function as far as we know. And the reason I say surprising is because this recipe is very general, right? It says all I need from you is some function that takes in any real number and outputs any real number. However, typically when working on quantum arithmetic, or maybe not typically, but oftentimes people try to implement very specific functions. So the fact that our general implementation somehow happened to be the most efficient implementation of e to the minus x, or at least the most efficient implementation that we know of, or that I know of, let's say, that was a little bit surprising, and maybe it'll be interesting for people to find better implementations. And that takes us to the last part, which is maybe the most interesting part, at least for me, is how things can be taken further. And hopefully there may be some ideas for some of you listening, if you want to get into the field and kind of get hands-on, there's some ideas that are out there. And of course, if you would like to know any more about any of these ideas, feel free to reach out. I'm always available to talk to. Okay, let me carry on for now then, and I will pause. I will definitely pause for questions as well. And again, feel free to interrupt me anytime. But having kind of gone through the introduction, today I'll be talking about this paper mainly. So everything I've talked about before kind of comes across in this paper. This was published in late 2022, and it was a collaboration between myself, Matthias, Martin, and Will, back when I was at Goldman Sachs. So it was a collaboration between Goldman and Microsoft. Okay, so let me maybe start with a brief overview of the work.
Can I ask a question?
Yeah, please.
Sorry, maybe I missed. You're saying that you will only describe how to efficiently implement e to the minus x, the exponential function, or is it a general algorithm and I can find out other functions to efficiently implement via this?
Yeah, thanks for that question. There are a few parts to that. So I will be describing how to implement any arithmetic function. However, I will look into this as an example of how much it costs. I will talk about the e to the minus x example of that. And the other aspect is, so although this implements any arithmetic function, it's not necessarily true that it's the most efficient way to implement that arithmetic function. It turns out for e to the minus x it is. But I think that's definitely something that's interesting to try and understand. Just to jump the gun a little bit, we know, for example, if you want to implement simple arithmetic functions like addition, subtraction, this is absolutely not the most efficient way to do it. But there's well, at least we know of one where it seems to be quite efficient, and there may be future work on understanding which classes of arithmetic functions this method could be very helpful.
And when you say efficient, do you mean efficient in storing the information or runtime?
Runtime. So, well, a little bit of both. So I guess
overhead and runtime.
Yeah, so number of qubits and the T count and T depth.
Okay, and efficient again is in the size of x?
Efficient in the size of x.
Polylog?
Sorry?
Guessing polylog x?
So there's actually, it's exponential. So it's not efficient in terms of asymptotically efficient, which is kind of interesting, right? It's just, so I overload this word efficient. So it's not, it's sort of, you can trade off between width and depth, and I'll get to that in a second, but it's not actually efficient asymptotically, but it turns out that maybe in certain cases, despite it being exponential, it can be, if the actual counting, the number of gates or the depth turns out to be lower. Yeah, it's kind of strange.
Okay.
And I will add one more thing, which was, I mean, I'm sure I'm going to talk about that one thing later, but I thought I'd say it now, but it slipped my mind. Maybe I'll get to it. Yeah, maybe I'll remember.
So I have one question, sorry. Like,
yes.
So with this exponent term, like this efficiency, it's like T get count or like depth and T get count together. I mean, I didn't get
yeah, so in this particular example of e to the minus x, we think it's both in terms of depth, well, in terms of depth and count and number of qubits, it's just the best thing out there.
Okay.
We think again, and again, since this paper came out, maybe somebody came out with something better, which would be great actually. Yeah, but we think it's the best so far out there.
Okay.
And oh, that was the last thing. And I'll get to the subtlety in a second. It also, the other parameter we'll have to specify is the error tolerance of your output, because, you know, e to the minus x is not a rational number. It's a real number. So if you want to describe it exactly, you need infinite amount of bits. Most times when using a regular computer, you don't really care because you have 64-bit precision. So you're like, okay, that's good enough. There are some instances where you do care, but they're very special. However, in quantum arithmetic, we also care about the precision, because we typically don't want to use 64 qubits for every single number we want to encode, because that makes a lot of qubits. I like these questions. Please keep them coming. It makes it more fun for me as well. And if I don't answer any of your questions satisfactorily, please do ask again, or you know, feel free to prompt me some more. Okay, so this is the thing. We created a method, or like a recipe, to implement any single variable quantum function. And at the crux of this recipe is something that we call the lookup table. I'll explain it a little bit. And it sort of is what it sounds like. And the implementation can be found, you know, in this paper. And this just says the lookup table. The concept of a lookup table was adapted from this work. And we implemented in Q#. Q# had nice inbuilt functions for fixed point representations. And it was also very nice at having resource estimations, especially in the fault tolerant regime. So it'll be like, hey, this is how many This is the T depth of your circuit, right? Especially when you're not implementing things gate by gate, you're kind of implementing things using fixed point representation operators and stuff. So it was quite nice. But again, kind of jumping the gun, one of the things that can be interesting for people to do is to maybe think of implementations in other languages. But let me talk about this lookup table. I think I'll talk about the lookup table, which is at the crux of the work, and talk a little bit about the extra facets, but not go so much into detail. And then, yeah, and then I'll move on to the real world use case. So the lookup table is composed of something called a select network. So let's talk about the lookup table first, and let's choose a very, very simple example. So again, it's always the case. I have some unitary operator acting on some input register and encoding the output on an output register. And I'm going to call my function f of x plus 1. That's my function. It's a very simple function. And in addition, I'm going to allow for only two inputs. Either my input is 0 or my input is 1. And so now you can make this lookup table, right? It's just a table that says on the left column, it's all the inputs. And on the right column, it's all the corresponding outputs. So 0 plus 1 is 1, or 0, 1. And 1 plus 1 is 2, or 1, 0 in binary. So this is a lookup table, and you want to turn this into a circuit, into a quantum circuit. And that's where you use this select network. And so you can do this by, I'm going to just walk through this. So you have your input qubit up here, and here you have your two output qubits. And all you're saying is you're saying, okay, if the input qubit is 0, then your output better be 0, 1. So if your input is 0, well, I don't do anything to the first qubit, or I've been explicit here and called it I for identity. And you put an X on your second qubit down here. And on the other hand, if it is 1, then do the opposite. Put an X in the first qubit and put an I in the second qubit. And that's really it, right? You can do things. So as you this round dot, for those of you who may not be familiar, means control on if the qubit is 0. And this you can always implement by adding an X gate, control an X gate again. So, but this is shorthand for that. And this is kind of all it is. And this you can kind of maybe start to see how you can do this for any function with any number of inputs and any number of outputs. So you can add more qubits to your inputs, and you can just add more controls, right? So if you have a 0 up here and you want to control on 0, 0, you say, okay, if the first qubit is a 0 and the second qubit is a 0, do this operation. If the first qubit is a 0 and the second qubit is 1, just do this operation. So this is it really. And that's why it's sort of a pretty boneheaded method, I think, to do something or to compute a function, let's say. And note that in this method as well, you pre-compute all the possible outputs, I guess the inputs you're given anyway, but you pre-compute all the possible outputs classically first, right? And so you say, I'm going to use my classical computer. And again, as we mentioned, if you just want to do quantum arithmetic, it's super fast to just do it on a classical computer. So you just do it there first, and then you have all the outputs pop up. So this is how you would do it, were you to build it from scratch. Our implementation, we have a wrapper function around this that just does this for you. We just ask for what is your domain and range, or not even range, because range is defined by the domain. So domain and input and function. So we say, what's your minimum value of X? What's your maximum value of X? What is the actual function? And then we'll tell you, it'll make this table classically and implement it all under the hood. Okay, maybe I'll stop here if there are any questions before talking about the select swap network and other things we put around this.
Yeah, question.
Please.
So what exactly is select network?
So it's this circuit on the right that you see. This is an example of a simple select network.
Mm-hmm.
And if you just add more qubits as inputs or outputs, it just gets a bit more complicated, but that's basically it. There's a little bit more in terms of you can be clever if you want to uncompute the select network. We don't really, you can uncompute it in a different way than just redoing the same input. There's a little bit of clever things you can do, but essentially this is it. It's a network that selects the answers, it selects the outputs based on the input.
And the input is the function definition, x plus 1?
So the input, I see. So the input to our function that we made is the function definition, but to the select network, it's you can think of it as there's a select network for each function, and the input is this top qubit here, right? It's the 0 or 1, and the output is 0, 1, 1, 0.
No, so the input to the select network is the table.
The input to the select, so the select network is a circuit.
Yes.
So the input is just this top qubit up here. And so it's just the input qubits, right? And if you have a different function, you'll have a different select network.
Sorry. Okay, we are confusing the word input. What I meant is if I want the circuit to be given to me, which computes the function fx. I
see. What is my input to that? Yes, that is also a function that creates a circuit. Yes. Okay. So that there will be, and I'll get to this a little bit as well, but there will be 3 things that you need to give me. First, you need to give me the function. That is correct. You need to give me the function. You also need to give me the minimum and maximum value of x that you are expecting. Yeah. And thirdly, you need to give me your error tolerances. And then actually there's a 4th thing where you can, but okay, no, for the select network, actually there's only 3 things. And then when you make a select swap network, there's a 4th thing, which I'll get to in a second. But yeah, those are the 3 things you need to give me.
And it's not unique, the circuit that I will get at the end.
It is, I think, because it'll always be it'll always be dependent on this table. So if you have this table, the way that I make it, you can always switch the order of these things. That's fine.
Yeah.
But the way we make it is we start with the lowest value and we go up to the highest value to define these control gates. So in that sense, it'll always be the same for any given set of those parameters.
Yeah.
Does that make sense?
Yes.
Okay.
I have a question.
Yes.
Sorry, this might be a stupid one, but why do you need a network? Sorry, why do you need a circuit if you have a lookup table? If you already have pre-computed it, I mean, what's the point?
Yeah, so the point is that, and that's sort of related to a little bit in the previous talk, and it's a good question. The point is sometimes you need to compute f of x in superposition, right? So you have some state in superposition, and you want to apply this unitary function in superposition. So you can't do that classically. So you need to have some circuit that can do that, and that f of x will be part of some larger algorithm that you need to do. So the question is how, if you want to compute some f of x, if you want to implement f of x in your circuit, and you need to do it in superposition, then what circuit do you use? Right, that's the question.
But then we need the classical calculation of all inputs already on hand.
That's right. Yeah, you need to perform, and you can perform this. You create this table on the fly when you make the circuit. So you have your classical computer, you give it the information, it creates this lookup table, and then it makes a circuit, and then it throws away the lookup table. And the creation and that whole process will be typically much less time than running the end-to-end algorithm. So it's kind of, yeah, and especially if you use this circuit in the end-to-end algorithm many times, you don't need to make the lookup table many times.
Okay.
Did that make sense? And I will definitely get to maybe more of an example in the next few slides. But yeah, if it doesn't make
sense,
thanks. Cool. Any more questions? Cool. So, okay, I mentioned this is a select network, and I use a simple example of a function, but maybe you can see that you could just do this for anything. And as Ankit mentioned, you have to use a classical computer. You pre-compute all of this, and after you can make this circuit. You can add additional things to this to make, well, you can add a few things to the circuit itself and also to the user to make their life easier. So the first thing we add is we turn the select network into a select swap network. Which was given here, which has come up with here. And the idea is that maybe I won't go through too much in detail, but you can reduce the depth of your circuit if you add more qubits. and the additional gates you add are swap gates. To kind of, I think maybe to just say it briefly, and if people are interested, I can go more in detail. But it's kind of like, instead of saying, okay, I'm going to compute what if I have input as 0, 0, 0, and then I have input as 0, 0, 1, and then I have input as 0, 1, 0. I say, okay, well, let's say the first qubit is 0. Then what are all my possible outputs for the last 2 qubits being 0, the last 2 qubits being 0, 1, et cetera, et cetera. So you compute, instead of computing 8 different possibilities for 3 qubits, you compute 4. And then you say, okay, well, now I'm going to take that last qubit, and if it's a 0, I'm not going to do anything. And if it's a 1, I'm going to swap out whatever answer I need to, because my like different answers are stored in parallel. So that was a very quick and wavy way of saying it. But essentially, the important part is that it can reduce circuit depth, but at the cost of adding more qubits. So that's another parameter that you can choose in this function, how much you want to change that. In addition, we have to deal with negative numbers. In my examples, and actually in all select and select swap circuits, you start with, okay, my input is 0, 0, 0, 0, and then the next one is 0, 0, 0, 1, the next one is 0, 0, 1, 0, et cetera, et cetera. So if you have negative numbers, right, and this depends on your encoding, your minimum value of your input is not 0. So essentially what you have to do is you have to create an adder circuit before that just shifts everything to the right a little bit. And finally, this is kind of the part that I was mentioning before, is you need to deal with domains and errors. So you need to know what your minimum and maximum possible values can be, and what your tolerances are for your error output, and also potentially your error input. There are some times where you're applying an arithmetic function on a register that already has some potential error in it. So if you want your output error you have your input error or something, you have your output error or something, and you have to make sure that if you want your output error to be some maximum number, and these epsilon ins and epsilon outs are the upper bounds, right? You give it an upper bound. Then it says, okay, I'll take into consideration the fact that the input is also not exact. And I'll do what I need to do to make sure that the output has at most this epsilon out value. And therefore, by giving in addition, so the function kind of, you can think of it as computing these, what combination of x's and identities I need. But the output is going to, the domain and error is going to tell me how many qubits I need to store my result. Okay, there is a question in the chat which I can read out. So for a single value quantum arithmetic function denoted by view, it takes in a quantum state n representing an integer n as input and returns a new quantum state f of n representing another integer as output. So is there a function that could be any arithmetic operation that preserves single valued property? So yes, so indeed, actually, it doesn't take in necessarily an integer n and output an integer n. It outputs, so as any quantum circuit does, it takes in a string of qubits and outputs a string of qubits. But the way you encode that, that string can represent different things, right? So just going briefly back to the first example here, so 0, 0, 1, 1 in integer represents 3. But in a fixed point register representation with p equals 2, which I can go into more detail if people are interested, it represents 0.75. So you can actually take in any, you can create any arithmetic function as long as you know what your register, how your values are represented in your register. Hopefully that answered your question, Abdullah. And in the meantime, I can also pause here to ask if there are any questions. So this, by the way, basically concludes how the function is implemented. There's in the paper, there's much more detail going through all the nitty-gritty bits and extra subtleties. But basically, we take a select network, we turn it into a select swap network, We add an additional circuit before to kind of shift everything. And then we do some pre-computations that help us determine how many qubits we need as the output, depending on what the error tolerances are.
One question, Rajiv.
Yes.
So like it looks like from this circuit, you are going through the inputs in the binary order.
Yes.
I think you can optimize a bit more by going through as a gray code.
Can you explain that? I'm not so familiar with the gray code.
So instead of going from 0, 0, 0, 1, 1, 0, 1, 1,
yeah,
you can go to 0, 0, 0, 1, 1, 1, then 1, 0. So at every instance, you're adding or changing, flipping only one of those multi-controls from a positive control to a negative control or vice versa. So for example, over here, the middle thing is going from 0, 1 to 1, 1, the next one.
Yes.
Yeah. So that's going, so you need basically 2 NOT gates for both those lines. So if you go at that step, if you go to 1, 1,
yes,
let's flip the last 2 blocks, then you can reduce the X count by 1 more. Like it's from another work from Craig Gedney, actually, that if you use gray code for these kind of encodings, you can like reduce the number of NOT gates in the multi-controls.
Interesting. So is it a, so that's reducing number of NOT gates. Do they talk about how, or do you know if how the impact of that in like a fault tolerant regime is?
It's not going to impact a lot because like it's still like the same equivalent function, except that you are just now going through the same number of input bits in a different order. So it just reduces those extra X gates.
X gates. Okay, cool. Yeah, then that's oh, there you go. Thanks for sharing that. Yeah, I didn't know that. Something people can think about if they want to continue working.
Yeah, he has a nice blog post in the Quantum Pontiff blog.
Ooh. Do you have the link by any chance? If you happen to have it, I don't want to make you scour the internet. Feel free to share it in the chat. That'll be pretty cool. Nice. Okay, any other questions about this general structure? Okay, there will be time at the end for questions, I believe. So I can keep going, and if people want to even dig in more, I have some backup slides and things like that. So I just want to talk a little bit about this lookup table method compared to maybe other arithmetic functions that are out there. It's very general. So as mentioned, you can implement any single variable arithmetic function. You know, you can have whatever function you want, even user defined. Like you can go to Python, put like def my function, and then have some output. And as long as the input is 1 float and the output is 1 float, that works, right? And that's because all the pre-computation of the lookup table is all done classically. So it'll just use that function that you created to pre-compute the lookup table. In addition, the circuit, at least in Q#, can be generated with 10 lines of code or less than 10 lines of code. So this is including like you add all the like, okay, this is my 1 line for like, this is my minimum and maximum, 1 line for this is my errors, 1 line for this is the trade-off, and etc. And then in 10 lines you have the code. The actual function call is just 1 function call, but you want to define a few variables before. The code, I have a backup slide with the code. I don't think it's so relevant, but I can bring it up if people are interested. Yeah, the other one is, so this idea we've talked about a little bit, where you say, okay, you ask the user for like the input and the output, the minimum input and the maximum input, in addition to the errors. It's quite nice, I think, because when you think, I mean, like, at least in my limited experience in quantum arithmetic, it's always been looked at in terms of, okay, here are the number of input qubits and here are the number of output qubits that you have. And so this is how expensive your circuit is, or this is how your circuit looks like. But tell us your number of input and output qubits. But typically when I'm thinking of an arithmetic function, I don't think of it in terms of bits or qubits. I just think of it like, oh, I input a number and I output a number. And okay, also that number can have some error room because of precision issues. And so I can just tell this like function in terms of like coding function that we made, these inputs, and it'll pop out the circuit you need. So it does all the other stuff in terms of calculating how many input and how many output qubits you need yourself. It does that under the hood. It's also nice because in addition to doing stuff under the hood, you have this aspect of being like, hey, this is the maximum upper bound or this is the upper bound in the error that I would like. And I think some things that, at least when doing stuff like resource estimation or trying to understand which algorithms can be useful, you typically have a use case in mind and you say, okay, I want to compute this. And I know that if the value of my output is within, 10 to the minus 3 or 10 to the minus 4, then I'm happy. Then it means it's like a good enough algorithm for my specific, let's say, industry use case. And so we also say, okay, good, then you can just think of it in terms of that, right? So for practitioners, I think it tends to be something that they like. And this last point was what I mentioned also earlier, that you can do a trade-off for whatever reason. If you want to decrease your depth at the expense of qubit count, or vice versa, decrease your qubit count at the expense of depth, then you can do it. So that is everything I want to say about the implementation before going on to an example of where it's used very briefly. But again, I can pause for questions if there are any. Okay, cool. So, oh, yes, please. Question. Yeah. No? Oh, maybe it was just by mistake. Okay, if there is a question, please feel free to interrupt me anytime. Okay, so now let's talk about important, well, or at least a relevant use case. So as mentioned before, they play an important but often costly role in end-to-end algorithms. So the use case I'm gonna talk about is derivative pricing. So derivative pricing is the idea of, say you want to sell a stock option. You're a bank, and you want to sell a stock option, any kind of stock option or any derivative it's called. You want to be able to say how much does that option cost for someone to buy. And the way you compute that typically is through Monte Carlo simulations. So the use case is, okay, well, you can maybe perform Monte Carlo simulations on a quantum computer. And the answer is yes, you can. And also that there is a quadratic speedup, which is, there's a debate about whether that's actually ever going to be useful or not. It may or may not be, and maybe I don't want to get too much into that at this point. But again, if you feel strongly about that, you can just take this as an example then. But the way the derivative pricing works is it's got amplitude estimation at its core. So you load in some distribution to your quantum computer. You then apply some function where you compute the payoff, and then finally you perform amplitude estimation on your final state, which then pops out the average. So by prepared distribution, I mean you kind of load in all the different Monte Carlo paths at the same time. And you compute all the payoffs of each path at the same time. But then when you want to, estimate the average, you would use amplitude estimation. You could also make a measurement, in which case you have many paths of your Monte Carlo system, and it collapses into one. You say, okay, great, I have one value. You redo the process, you measure again, you collapse it. It takes another one. You take all those values and you do, like classically, you compute an average. But that sort of defeats the purpose of any speedup, because you can do that classically anyway. So in order to get your quadratic speedup, instead of doing a measurement and storing that number and doing it many times, you just use amplitude estimation. So that's kind of the use case. And it turns out that in preparing this distribution, and so by the way, if any if there are any people that want to know more, you can have a look at down here. And I think, oh, I maybe could have put the YouTube link to the talk as well. But if people are interested, just feel free to ping me and I can put the link to the talk that discusses this use case a bit more. But when you prepare all the paths, it turns out there's a step where you have an input and you want to compute e to the minus x, or e to the x, sorry, of all those different paths. And that is a very expensive step. It turns out that just this one computation, and there are many other computations when preparing the distribution, there are also other computations when computing the payoff. And in amplitude estimation, you essentially reuse these computations a lot. You perform these first two steps repeatedly along with some other steps. So with doing that, actually every time you still have to do e to the x, and that accounts for roughly like half the number of qubits required is because of this step, and then the t depth as well, half of it is roughly half of it is because of this step. So this is an example where quantum arithmetic, and we actually used, we talk about it more in the second reference in this blog post of how we use this lookup table method to compute e to the x, and it helped trying to reduce resources. Okay, there's a question by Abdul.
So I had a question. So as comparison to like other numerical methods, like maybe you've heard about like the finite difference or lattice based method. So how does quantum Monte Carlo simulation like fare in terms of accuracy and computational efficiency for solving derivative pricing problem?
Yeah, so sorry. Yeah, so that's the way we approach the problem is actually the opposite. We say, okay, we need some sort of accuracy, like because we approached it from like a use case method. So we went up to the business, we said, hey, give us an example of a derivative that you think is pretty computer intensive or compute intensive, and also what accuracy do you need it at? And we know that asymptotically, like algorithmically, no matter what those numbers are, it just goes quadratically faster than the regular Monte Carlo, right? And I'm not talking about quasi Monte Carlo processes, but it seems like for quite complicated derivatives, sometimes people don't use quasi Monte Carlo, they use just Monte Carlo. And so doing Monte Carlo on a quantum computer just gives you a quadratic speed up asymptotically. But what we said is, we said, okay, fine, it's some speed up asymptotically, but when actually implementing it, how does it work? And the way we tackled your questions, we flipped it around. We said, okay, tell us what the precision you need is, and we will tell you what the circuit looks like and how long and not how long it takes to run, but what the circuit looks like. And then the hardware people can look at it and be like, okay, this is the T depth, this is the qubit count. And so we estimate that in the era of fault tolerance and however many years it might take this amount of time. And that's generally how we approach these resource estimation things.
And one more question, like, so does the choice of basis sets or wave functions like plays a role in the simulation for pricing derivatives?
The choice of which basis set?
The computational basis sets.
So do you mean for which?
For Monte Carlo simulation.
I guess I don't, maybe we can talk offline because I'm not quite sure I understand the question, because there are many parts in the quantum Monte Carlo. So I'm not sure what you mean by a basis set.
Yeah.
But yeah, definitely ping me later and we can talk about it a bit more.
Yeah.
I mean, I have a very like ground level question. Maybe it's a bit stupid, but still, like how making a function which projects from 0 to e to the power x connect to derivative pricing. I'm sorry, like I didn't understand.
Can you repeat that? Sorry, how does the function? I just missed that.
Like how does this function, creating this function which projects from this, transform from this ground state to e to the power x is connected to derivative pricing? Like how?
Yeah. But by the way, like I find oftentimes that people that say, oh, I think this might be a stupid question. It turns out to be a very good question. So I appreciate that. And so this is also a very good question. So the thing is, so what you do is actually, to be a bit more precise, here you compute the log of your price in these, and to change it from, so you have to be, oh, my smart shutters are being not so smart. I apologize for that. You typically, what you do is you simulate your stock, but you simulate usually the log returns of your stock. And in order to change your log returns to returns, because you use geometric Brownian motion, for example, you need to, your final returns, your final log returns, you need to compute e to the power of that to turn it from log returns to returns. You can think of it like, maybe it's like, oh, your simulation, it's much easier to simulate things if you just have the log of the price. So you simulate the log of the price, and at the very end you say, okay, now I just need to do exponential of that to turn it into actual price. Okay,
it makes sense. And also, like, what do you mean by computing payoff? Like, what is this payoff?
Yeah, that's also in terms of the specific use case. So a derivative or an option says something like, oh, okay, I will give you, it's kind of like a bet, right? You say, okay, if a very simple example is a binary option, where you say, okay, well, in 3 months from now, if the stock of some company is above $10, I'll pay you $2. But if it's below, then I don't pay you anything, right? So that's the bet. So the payoff says, okay, well, this whole first thing simulates the price of the actual stock, right? So it tells you, oh, at the end of this whole simulation, the price of the stock could be $8 or $2 or $11 or whatever. And the payoff is, okay, given that I have these potential ways that the stock price can go, what is the actual money I get from the bet? So in this case, you have a stock that wiggles and it ends at $11. Okay, then the payoff for the $11 is actually just $2, right? Because I bet that if it's above $10, I'll give you $2. Right. And you wiggle, and if it's $8, then it's 0, right? So that payoff is just changing from price to like actual payoff.
Exactly. Okay, I see.
So it's yet another arithmetic function. Actually.
Okay, thanks. So you're saying that in this problem, the main bottleneck is basically the preparation of the distribution. The payoff can be computed efficiently, right?
Yes, exactly. Or at least, yeah, so to actually going back to be careful with the word efficient. So again, not asymptotically efficiently, but just with fewer gates, including the overhead. Yeah, it turns out in this case, not only is it the preparation of distribution, it's literally this one step is the biggest bottleneck. I mean, there are other steps which are also expensive, but you take this one step. Let's say so part 3, you can essentially think of it as doing part 1 and part 2 again and again. Within the preparation of the distribution and the computation of payoffs, there are many such, mainly, but not always, arithmetic calculations, and there's some other calculations too. But within all those steps, this one step of just going from here to here takes up half your resources. So yeah, it's kind of an annoying one.
Yeah. Okay, thanks.
Also, full disclosure, there, like, regardless, this whole, yeah, actually, no, maybe I have nothing more particular to say. We can go down more into the derivative pricing example itself, but yeah. Okay, so what do I have next? Oh yeah, so any questions on this? Actually, any more questions on this before I go and talk a little bit about some of the results? Because I've kept saying less expensive, more expensive, but maybe I can add some numbers to that. So that's what I want to do next. But maybe I can also pause for any more questions. Cool. Okay. So here are some numbers, and we have other functions that we have examples of, which I have in the backup slides, but maybe this is the most interesting one because also it's the one where we were like, oh wait, this is quite efficient. So we said, okay, what if you use this, again, general method, right? So just to iterate, this is a method. You compute this classically and you build a circuit in a very kind of step-by-step manner where you just build one output for every single possibility. And we get this. So let me talk about this table a little bit. This is the function that we want to implement, so e to the minus x. This is the minimum and maximum values, and these are your allowed input and output errors. We just chose these values based on the previous work. The Poirier method seemed to be the most efficient way to do this, at least at the time. And so this LUT means our method, and the Poirier is the Poirier method. They unfortunately don't do t-depth, so it was a bit hard to know exactly what the t-depth was, but given that the t-count is much less, and this is not like super highly parallelized, it's safe to say that that the t-depth was also better. But you can see that basically you get something like, I don't know, factor of 5, maybe an order of magnitude better, like in this specific case, right? And it's kind of interesting because it does depend a little bit on the actual, you know, range and domain. So there's more work to be understood in terms of how exactly it depends on these things. I mean, we know that, okay, sorry, not the range and domain, the error and the domain. We know, of course, you know, okay, if you want if you want less error, it'll take more resources, but even the domain factor and things like that, there may be interesting things to think about there. Oh, and thank you. Arithra has posted the gray code idea. Very cool. Okay, so honestly, we did a couple of more such examples for e to the minus x squared, and what was the other one? Sine of x. I have to look at my backup slides. I think it was sine of x or arc sine of x. No, square root of x. Sorry, square root of x was the other one that we did. Those ones. So, for example, square root of x. Typically, for most cases, the bespoke method, or the method that was used to only compute square root of x, was better. For the e to the minus x squared, it was interesting. There was a little bit of a mix in this table. It looked like this, not the numbers, but the table looked very similar. And there were some values that were higher in the Poirier method, so more efficient in the LUT, but sometimes it wasn't the case. So that was kind of interesting as well. Yeah. So I kind of wanted to, so now I wanted to talk a little bit about how much time we have. Okay, I wanted to spend, I think I have just 1.5 more slides left on talking about what other work people can do if they're interested in taking this type of stuff forward. And some of this work, you know, it doesn't have to be that you have to read and understand the whole paper to even start working on it. You can work on it kind of a little bit off the bat. So the first one is implementing such a method in Qiskit or Circ or any other software package you think is useful. This is, of course, a nice way to contribute to the open source. It's also typically, I find, when re-implementing things, you sometimes find little improvements, or maybe even a big one, just because while you're re-implementing, you're thinking of something and you're thinking, oh, well, maybe what if we do it this way? And then suddenly that little improvement, you're like, oh, nobody else, or at least the previous work didn't think of that. I can add that, right? There's, especially with these swap gates, there's things that we definitely know we can be a bit more careful about and think about. I think the way to do this, especially if you're very new to this, is just start by, you know, do something like implement this first. Just implement this very simple circuit and try it for different outputs, and then you kind of grow to make it, okay, let's do it for any general function. And then you can incorporate the errors, and then you can do a select swap, like do it like that. I think it's, you know, definitely do it step by step. And even things like, even if you implement just the lookup table, for example, I'm not sure if the lookup table function even exists in Qiskit. Like you could say, okay, I need as input the whole set of, I need the input to my function, like the function that I write in Python. I need it to be a table where with all the input values and output values, and now I'll output a lookup table for that. I don't even know if that exists in Qiskit, for example. So there's definitely ways to get going. Okay, so there's other ways to use this work. You can use it as a baseline. So if you come up with your own method for a quantum arithmetic function and you want to write a paper about it, a nice thing is you can just be like, okay, let's use this generic or this generalized version that exists in C# as a baseline. So you can be like, okay, at least we're not very inefficient. We're better than like a method that is just a catch-all. Okay, the third point I kind of mentioned in conjunction with the first point. While you're implementing it, you can improve some things. You can extend the method to make it a multivariate arithmetic function. So instead of just taking in one input registers, you can take in 2 input registers. It's almost the same thing. It's just a little bit of logic that you need to change. But there's not such a conceptual difference. You can also extend it to implement other representations. As I mentioned, it takes in a fixed point representation currently. You can do it for other representations. You can also work on a slightly more theoretical side of understanding the error propagation, especially if, I think one example could be if you have, let's say, and this doesn't even have to be just the LUT method, by the way. If you have several arithmetic functions back to back, and you say, okay, I need my output error to be a maximum of this amount. You have some upper bound. You can distribute the error among these functions, however you will. Theoretically it doesn't change, but maybe making one function much more precise and the other function giving it more leeway can change the number of gates as opposed to doing the opposite. And so you can make it more efficient, and again, not asymptotically efficient, but you can reduce the overhead maybe that way. And the last point I have here, and I'm sure there are other aspects that people can think of, but is to understand the class of functions for which the lookup table is the most efficient. So as mentioned, like we know that for very simple functions, like addition, subtraction, these are not efficient. The lookup table method is not very conducive for those. They're much better methods that are already out there and easier, honestly. But for things like e to the minus x or even e to the x, I believe, turns out maybe this lookup table is efficient, or not efficient, but again, lower cost. And yeah, and there may be some clever ways to think about which functions this is conducive for. So everything I have talked about mostly is in the paper. It's self-contained, and the code is also publicly available. The GitHub link is, I think it's easiest to find it in the paper, and you can just click on it. It's actually a footnote in the first on the first page. There's a GitHub link at the bottom. Okay, just if you will humor me for maybe one more minute. I like to change gears at the end of my talk and talk a little bit about the fact that in quantum technologies and in technology fields in general, we have a lot of very talented people from different backgrounds, but there's sometimes not as big a diversity as we'd like. And so I think there are but I'm long-term optimistic about this. I think there are people that care about this and that are working hard to improve the diversity in our field. But there are also people that are from diverse backgrounds that are just very good, right? And so I always like to flash a slide, and I change these names, occasionally, but just to show you, like quantum scientists, they come in very different forms. All these people, they look different. They are from different backgrounds. They have very different personalities, but the thing they have in common is they're all very successful as highly technical people in the field of quantum science. So I just wanted to throw that out there. And they're also, yeah, feel free to reach out to them as well if they're available. They're very cool people. Okay, I'll end with this slide. Thank you for humoring me. I'll get off my soapbox. And always happy to answer any questions.
Yeah, thanks, Rajiv, for the amazing presentation and the discussion. So I have like one question about this. So you said in the initial, when you were discussing the lookup table, that if you increase the number of these input qubits, right, then the depth decreases. So you can just use it, right, to decrease the depth of this circuit, like the fourth point. So that was your motivation in this, like you can increase like x, y, 0. Yeah,
that's right. You just increase the number of input qubits. It's not so, yeah, was that the question, or did you have a follow-up on that?
No, this is just like, this is what you're trying to point out. So that's why I was telling this point.
Yeah, that's right. It's just simply increasing the, yeah, that's right. From a circuit point of view, all you're doing is increasing the number of qubits, right? I think honestly, to extend the method to a multivariate arithmetic function, it's actually an extension on the classical part where you compute this lookup table. And so that's the part that you have to kind of change or massage. And, you know, you can ask the user things like, okay, in addition to giving me, you know, your function that you want me to compute, also tell me how many inputs it has, things like that, right? So to make it easy to the user, but you're right. Otherwise, it's just basically just increasing the circuit-wise, just increasing the number of input qubits.
Yeah. Interesting. So there is always this trade-off, right? This depth or number of qubits.
Yeah, that's this this one. So I haven't gone so much into it, but it's essentially you can replace some of the select part with swap parts. That adds more qubits, but yeah.
So I was also wondering, like, is it possible that if consider like there is a machine learning model or something, and you give up this lookup table and it just find out this particular quantum circuit efficiently, depending on some cost function or something, right? In this derivative pricing.
Yeah, I have not thought of that at all. That sounds like an interesting idea.
Yeah, I mean, I was just thinking like that because, you know, there are many redundancies in the circuit, possibly, and it's not always possible to look at the circuit and find out this redundancy, right?
Yeah, and I think this is interesting as well because arithmetic functions aren't so, yeah, they're not so complicated. Like they might not need such a big Hilbert space. But okay, now I'm getting a bit ahead of myself. I'm not sure. But yeah, that's interesting.
Yeah, so I had all my questions done, and thanks for the explanation. So anyone want to ask anything, just unmute yourself or write on the chat.
I really like this last suggestion from Akash that like given this recent success of Alpha Dev, which found just a very small routine which is used a lot in linear algebra and classical computation. So like arithmetic functions, if you like optimize it even slightly, since they are used so much in part of like, for example, oracles, optimize like using a lot of cost, like machine learning cost to optimize it, it can be like really helpful.
Yeah, well, at least two well-known people agree. I'm happy. Yeah, maybe let me ask you, like, out of this technicalities question. So what are you currently working in, Rajiv?
What am I currently working on? That's a good question. I guess right now I'm looking into just a couple of things related to like machine learning and optimization. I think there's a bit of reinforcement learning that I'm working on, and a bit of a little bit of quantum computing for like drug clinical trials and things like that. But I should caveat this with it could change at some point, just because again, this is very an exploratory phase. So there's like these two things, and there's also other things that we're looking at. And I think before really, this is not at the stage where I'm really digging my teeth into it yet.
Well, I need to contact you then, because I'm also working a bit on reinforcement learning and GQE, not like very big problems and stuff, like optimizing the answers and stuff. Maybe we'll talk about this.
Yeah, for sure. I mean, yeah, including your recent paper that you put out. So
yeah, but it was really specific, you know, not like general method specific. But anyway, that's really interesting. And I think like there are many companies who are focusing on particular drug discovery stuff, right? With machine learning. Yeah.
Yeah, that's one of the things that we're let's say we're doing preliminary work on. I think yeah, it's at the stage where we're doing preliminary work on a few things, and then we'll see which ones we want to take forward.
Okay. So any questions, guys? Okay, so if not, then maybe I will just stop the recording. So Rajiv, thanks once again for this amazing talk, and we hope to get you as a speaker once again in Qoffee, and it's always amazing to have you, right? So,
Thank you.
Yeah, let me.
I appreciate that. I always like being among all the great other coffee speakers, right? They're really, yes, you get some really good people on here, so it's nice to be at least part of that gang.
Yeah, exactly. My pleasure.